Right, hello everyone. Welcome back to our second chemistry Olympiad training. Now we should be on page 10 of the previous set of notes and we will continue from there on. Now page 10 introduces us to this concept of ionic bonding, which you have done with your chemistry teachers in Sec 3. Ionic bonding involves a metal losing valence electrons, and in the process of losing valence electrons, the metals will form positive ions. Now, positive ions are known as cation ions. The way to remember is that cation ions has a T inside, which is like a plus positive charge. So metals lose valence electrons to form positive ions, while non-metals will gain valence electrons and form negative ions. Negative ions are called anions. So basically, you will form an ionic compound which has positive and negative ions if there is a metal and a non-metal. So this is a very simple way to deduce whether something is going to be an ionic compound or not. Now, why do the positive and negative ions attract each other? The positive and negative ions are oppositely charged, and therefore they are attracted to each other by strong electrostatic forces of attraction. So for example, over here we have the Mg2 plus cation. So Mg2 plus is formed when magnesium, which is in group 2, loses 2 valence electrons. On the other hand, the Cl minus chloride anion is formed when chlorine, which is a non-metal, gains 1 valence electron. The purpose of losing and gaining valence electrons, it is to achieve a fully filled outermost shell. Now, once they have formed their ions, you realize that they are attracted to each other, and these forces of attraction are called strong electrostatic forces of attraction. This word electrostatic simply means positive attract negative. So over here we have a positive Mg2 plus ion attracting a negative chloride ion. Now, the MgCl2 ionic compound doesn't just consist of one Mg2 plus and 2 Cl minus. Now, this is quite logical simply because MgCl2 is a huge crystal. It's a giant ionic lattice. This means that the ions in MgCl2 cannot just be one Mg2 plus and 2 Cl minus. There are many ions. So what the giant ionic lattice contains is Mg2 plus and Cl minus in a 1:2 ratio. So the ionic lattice basically might contain 1 billion Mg2 plus. If there is 1 billion Mg2 plus, then there will be 2 billion Cl minus ions. So the formula MgCl2 does not mean that there's only one magnesium, 2 chlorides. It means that magnesium and chloride are in a 1:2 ratio. We need to understand this key difference. Alright? When we say that it's in a ratio, it could mean there are billions and billions of ions, just that the ions are in a 1:2 ratio. Alright, which is the case for a giant ionic lattice. So the giant ionic lattice is the name of the structure for an ionic compound. Now let's delve deeper into the ionic lattice. So some properties of the giant ionic lattice structure. Number 1, they will have high melting and boiling points. As you have learned in Sec 3, the high melting and boiling points for the giant ionic lattices is due to the large amount of energy needed to overcome the strong electrostatic forces of attraction between the positive and negative ions. We will return to this in a very short while again. But the idea is to melt or boil something, you need to take in energy to overcome the forces of attraction between the particles. In this case, because it's a giant ionic lattice, therefore the forces of attraction are strong electrostatic forces of attraction between the positive and negative ions. Another very distinctive property of ionic compounds or giant ionic lattices is that they do not conduct electricity in the solid state, but they conduct electricity very well in the aqueous and the molten states. Now, aqueous means it's dissolved in water. On the other hand, molten means that it's melted. You have heated it up until the solid has melted. That's called molten or liquid state. Now, why is it that ionic compounds do not conduct electricity in the solid state? Electricity has to do with whether the charged particles are free to move. In the solid state, the ions are held in fixed positions by strong electrostatic forces of attraction, and therefore they are not free to move to conduct electricity in the solid state. There are no mobile charge carriers. That's another way to phrase it. However, once it's melted, molten, or dissolved in water, aqueous, the strong electrostatic forces of attraction have been overcome. As a result, there are free moving ions to conduct electricity. We say there are mobile charge carriers present. And finally, ionic compounds like magnesium chloride, sodium chloride, they are soluble in water, mostly, not all, but mostly ionic compounds are soluble in water, with some exceptions. But more importantly, they are insoluble in organic solvents like oil. Another organic solvent that's quite commonly seen in the chemistry Olympiad, hexane, benzene. These are examples of organic solvents which are commonly used in experiments. Alright, so your ionic compounds will be insoluble in such organic solvents. So we have gone through the main physical properties for your giant ionic lattice structures. Now let's delve deeper. We delve deeper into the property of melting point, because we know that melting point depends on the forces of attraction between the particles, in this case the ions. What will affect the strength of the forces of attraction? If we know that the forces of attraction are electrostatic forces of attraction between the positive and negative ions, we can come to the conclusion that the strength of this force of attraction clearly has to depend on the charges. The higher the charges on the ions, the larger the charges on the ions, the stronger the ionic bonds will be. Besides that, the radii of the ions will also affect the strength of the ionic bonds. The smaller the radius, the stronger the ionic bonds. So let's summarize. Higher charge, stronger ionic bond. Smaller radius of ion, stronger ionic bond. So importantly, I think we need to know these properties. Higher charge, stronger ionic bond. Smaller radius, stronger ionic bond. Alright, this is encapsulated in this equation shown on your notes. This equation tells you the lattice energy. The magnitude of the lattice energy tells you the strength of the electrostatic force of attraction or ionic bond. So now we can do the question 1. So we have two ionic compounds, lithium oxide and sodium oxide. We have to decide which one will have a higher melting point. I'm sure you can first write out the ions present. Once you have written the ions present, you realize that the difference lies in lithium versus sodium, because the oxide ions are the same in both situations. So what can you say about lithium versus sodium? The charge is the same. Both have a 1 plus charge. However, in terms of radius, the lithium ion, Li plus, will have a smaller radius. How do we deduce this? We look at the periodic table. Li plus has an electronic configuration of 2. We know this because lithium is 2, 1. It loses 1 electron. Therefore, Li plus has an electronic configuration of just 2. This means that Li plus only has the first shell. On the other hand, sodium, which has 11 electrons, is 2, 8, 1. After losing the 1 valence electron, it will be 2, 8. You can clearly see the sodium ion has 2 shells. Therefore, we can conclude, in comparison, Li plus must have a smaller radius than Na plus. So same charge, but smaller radius. So now let's go back to our equation for lattice energy. Same charge, however, the radius is smaller. If the radius is smaller, the denominator of the fraction is smaller. And therefore, the value of lattice energy is higher. So lithium oxide should have a higher lattice energy due to the smaller ionic radius of Li+. If it has a higher lattice energy, the melting point will also be higher. Simply because lattice energy reflects the strength of the ionic bonds. This means that with a higher lattice energy, lithium oxide has stronger ionic bonds, and therefore more energy is needed to overcome the electrostatic forces of attraction between Li plus and the oxide ion. Okay, so we have done A. Now we can look at B. So again, we are going to go through the same analysis. We will write the ions out first. NaCl versus Na2O. NaCl contains Na plus and Cl minus. Na2O, sodium oxide, contains Na plus O2 minus. These are the types of ions present. Notice I've only written Na plus once for Na2O because we are looking at the types of ions. Alright? Now you realize that the Na plus is the same in both cases. Therefore, we don't compare the Na plus. No point. We should instead compare the Cl minus with the O2 minus. And it becomes immediately clear. O2 minus has a different charge. It's doubly negative. So we say O2 minus has a higher charge than Cl minus. Remember, we are looking at the magnitude of the charge. Magnitude means I just look at the number, not the sign. So O2 minus has a higher charge because it's a double negative charge. Not only does it have a higher charge, O2 minus also has a smaller radius. You can again look at this from the periodic table. O2 minus only has 2 shells of electrons. Cl minus has 3 shells of electrons. So all in all, O2 minus having a higher charge and smaller radius results in Na2O having a higher lattice energy. Than NaCl. So if there's a higher lattice energy, the melting point of Na2O is higher than NaCl. So sodium oxide should have stronger ionic bonds and therefore require more energy to overcome these strong electrostatic forces of attraction in sodium oxide. Therefore, sodium oxide should have a higher melting point than sodium chloride. Alright? Now, I will leave part C for you to think about the difference between magnesium chloride and sodium chloride. But today's lesson, we have seen ionic bonding. We know ionic bonding is a strong electrostatic force of attraction between oppositely charged ions. We have also seen how this term, lattice energy, can be described in terms of the charges on the ions as well as the radius of the ion. We also learned that lattice energy is a reflection of the strength of the ionic bonds. So this is something that I hope you will come back to and rationalize. And it should be easy to rationalize once you have understood that ionic bonding involves electrostatic attraction between oppositely charged ions. Therefore, the charges as well as the radii of the ions should affect the strength of the ionic bonding. Alright, and that concludes our first video on ionic bonding. Please move on to the next video on covalent bonding. Thank you.